Look just briefly at the Bessel equation, which is this one right here, xy double prime plus y prime plus lambda xy equals 0. So this is an example of a Sturm-Liouville problem where we allow a 0 of p to occur at one of the boundary points. So in particular for x equals 0, there's going to be one right here. So this, oh, I forgot to write, we're looking at this on the interval, some interval of length r here. Now, in the case when there's an internal 0 of p, that's called a turning point. That actually turns out to be a very difficult and complicated problem, so we're not going to get into that here. But we will be looking at the Bessel function further in the next chapter or two. Bessel functions tend to pop up when you're looking at problems dealing with radial symmetry. And so, in fact, that's why I've got this as the interval from 0 to r, because we're going to see that this is actually talking about a radius. Anyway, more on that later. For now, let's just notice that we can reconfigure this as a Sturm-Liouville problem with xy prime and a negative sign being equal to lambda xy. So there's our Sturm-Liouville self-adjoint reformulation, and so we're going to take y of 0 to be bounded, and y of r to be equal to 0. So this substitution right here of boundedness for a value at the point where p is equal to 0, that's a common requirement instead of setting equal to some particular value. Okay, let's check self-adjointness real quickly. So if we have ULV minus LUV, then since this is in Sturm-Liouville form, again, we can use the shortcut of Green's identity. And so this is P times the Wronskian, evaluated from 0 to r. And so for us, P is x, and the Wronskian of U and V is going to be uv prime minus u prime v, and that's from 0 to r. And so evaluating this is going to give us, let's see, actually, let me write it on the next line here. We'll have at r, we'll have r times, and then oh, that's right. So u and v satisfy the boundary conditions. So in particular, u and v are both equal to 0 at r. So we'll have 0 times v prime r minus u prime r times 0. So that will all dry up and vanish. And then we will have, evaluating at 0, p itself is going to kill off everything else. So this will be the uv prime minus u prime v evaluated at r portion of the show is going to get killed by the 0. Okay, so we have self-adjointness. So let's see now, if we go ahead and solve that equation, actually it needs to be done with a power series technique. So using power series or method of Frobenius or whatever you want to call it, what do we get? Well, we end up with y looking like a linear combination of something we'll call j naught, evaluated at x square root lambda, plus b times something we'll call y naught, because hey, why not, evaluated at x root lambda. But it turns out that this one is unbounded at 0, heads off toward minus infinity. So let's ditch that one So only J naught, and so let me write the formula for it real quick. So expressed as a power series, it's minus 1 to the n z to the 2n over n factorial 2 to the 2n. So only this guy is bounded at 0. So let's see. So then we have our initial condition, or sorry, our boundary condition that the function needs to be equal to 0 at r. And so then we're looking at a times j naught r root lambda. And so then that implies that r root lambda has to be one of the zeros of the Bessel function. And so what are the zeros of the Bessel function? Well, those have to be crunched numerically. There's no explicit expression for those. Like Z1 is something like 2.405 something or other, and Z2 is 5.520 something or other, and Z3 is 8.654 and so forth. So whatever those zeros are, we'll need them. And then the eigenvalues that we get are going to be a Bessel zero divided by r quantity squared. And then we'll also have the corresponding eigenfunctions, which will look like a Bessel of then x times Zn over r. All right.